Okay, so if you go to rucalc.wordpress.org, or sorry, .com, just rucalc.wordpress.com. I'll probably send you an email with this link. A lot of what's on Blackboard is what's here, but also so I record Section 2 and Section 5 lecture. So they're very similar. There might just be a few different things. So the organization's a little bit different. So if you want to see the notes from Section 5 over this date, it's the same thing. It's a PDF, just like you guys only have access to your sections, though. So this would be on Blackboard. So, and this is just, it might just save you, you don't have to sign into anything, and you should be able to just pull up the video. However, the videos do not work in Google Chrome, so keep that in mind. And then you can, make this full screen and you can see the lecture. You can increase the speed or decrease the speed. You can skip ahead. So if you're like, okay, I don't understand this part of the lecture, you can skip there. Sometimes it takes a minute to kind of load. It's not horrible, though. Sometimes once you get there, it'll just kind of take a minute to kind of buffer up. And, of course, you can kind of skip ahead to that. So this will also be, if I go to rucalc.wordpress.com, I also have the lectures, Dr. Delaware's videos. So if you're like, I want to see someone else explain, we've already done that one. I want to see someone else explain the inverse of trig functions, or logarithmic differentiation, or derivative of irrational powers of x. Maybe logarithmic differentiation you're a little shaky on. This will take you to the point in Dr. Delaware's lecture that he's talking about logarithmic differentiation. So if you go to, that's also on Blackboard, right? You have access to that. So it might just save you guys one step from not having to sign into Blackboard. But it's also for anyone in Calc 1 that doesn't have access, because you're the only my students have access to all the material that's on Blackboard. So you can share this link with your friends that are also in Calculus. I'll actually be sending an email out later today to everyone in Calc 1 that can have it. It can take you to the message boards we have here. You'll have to go ahead and sign in. And I thought I fixed this to take it to our message board, so that might be something I need to tweak. Old final exams, I'm working on putting them there. They're on Blackboard now, but by the end of this week, they all should be up there. And then maybe supplements for engineering, or eventually we'll have like Pencast recordings of solutions of certain problems. And then before class, a couple students were talking about how to sign up for one-on-one tutoring. So the math science tutoring, I think they call themselves, they used to be called the MRC, now they call the MAS, I don't know what they named. They change their name every other semester. So here it's called TutorTrack. So you have tutortrack.umkc.edu. That's also, if you go to tutoring information, it gives you the link here, TutorTrack. For some reason, you have to copy and paste it into another, you can't just click on it. Again, I just kind of threw this together and it hasn't been tweaked perfectly, so as we go through it, hopefully I can work out some of the bugs. But you can sign in and sign up to see when a tutor is available to meet with you one-on-one. So if you go over there, you might not find someone to help you, or they might be busy helping a group of people. But if you want one-on-one, you can sign up for a time on tutortrack.umkc.edu. Okay, so there's just some resources for you. Does anyone have any questions on Wiley? There's some errors. Wiley reported they fixed 2 of the errors about an hour ago this morning, but I just found another one today in class, or last class. One of the sections we did had an error. Does anyone have any questions on the assignments? 3.1 and 3.2 was due. 3.3 is not quite due yet.
I think it was the second one on 3.1.
3.1, the second one. The first one did have an error, but they said they fixed it. This one potentially had an error. Yeah, if you send me an email, generally I'm about 15 emails behind. But if you send me an email, I will get it. It's something that doesn't go away until I click on it. And generally, if it's something I need to fix in your gradebook and I fix it, I'll just send you an email back saying fix, so you know that I've gotten to it. So if you haven't gotten an email back from me, it's still marked unread in my message box, and I'll get to it eventually. I should have time later this afternoon to get to it. So when that happens on Wiley, don't get frustrated. Take 2 seconds, send me a quick email, and then I can evaluate it later on, and you can come back to it. And then I will always respond telling you what I did. Like, okay, this is what you did wrong, or yes, you're right, here's your points back, type things. Usually it's pretty quick. Yeah, I fixed it, here's your points. You understand implicit differentiation?
Yeah.
Ideal? Yeah. You'll have some practice on your take-home quiz today. I think there's a couple of them on there. So, yeah, sometimes inputting it's rough. Another one some students were having issues with, really doesn't want the back button, was on the assignment, I believe it was 3.2, the ln of x plus 1. Yeah. This is saying ln of x plus 1, not ln of the quantity x plus 1. What is the derivative of ln of x plus 1?
1 over x plus 1.
It's 1 over x plus 0. The derivative of ln of x is 1 over x, and the derivative of 1 is 0. So this is not ln of x plus 1, it's ln of x plus 1. So you've got to be a little bit careful when you go to input the derivative, right? Because I get 1 over 8 times the quantity ln of x, and it gives me that parenthesis. I have to go to the other side plus 1. And then to the power minus 8 over 9, right? Times the derivative of the inside, and the derivative of the inside is simply 1 over x. So you guys see that? Go ahead.
I got that, but it might
And it
not.
doesn't accept it?
Well, I kind of simplified it, so it's 1 over all that,
Mm-hmm.
but it wouldn't accept it.
So you wrote,
Wait, is that supposed to be 8 to the 9? Why is that?
because,
Isn't it 7 over 8?
yeah,
Yeah, it's
sorry.
7 over 8.
In the previous class it was 1/9, so yeah, so this would be 7 over 8, minus 7 over 8. So you said
So
you
I
put
typed
in,
it as 1 over 8x times all that
Mhm.
to the
so
7
so we have 1 over 8x times the quantity ln of x plus 1 to the
over,
7 over 8.
the 1's supposed to be on the other side of these parentheses.
Oh yeah, that's a 1. Thank you. Yes.
I didn't know that.
Yeah, you put it in parentheses.
Yeah.
Did you send me an email?
No.
Yeah. If you have some tries on this one, you can go back and fix it. If you're not, send me an email.
I don't, because I did
Yeah,
it that
just
way.
send me an
I was
email
like,
then.
why isn't it- Okay.
Yeah, but do you see here that this is saying ln of x plus 1, not the ln of the quantity x plus 1.
And see, the answer doesn't even show it in parentheses, the x.
The x, yeah, because really you don't need the parentheses there. It's just understood that just the x. But however, every time you type ln, Wiley
how it
automatically
went in,
gives
right.
you the
And
parentheses.
that's what I was-
So it's just ln of x plus 1. So this was on 3.2. 3.2 was due last night. Is that correct? So yeah, if you have this problem, send me an email. And just let me know. A lot of students did that ln of x plus 1, so I can go
Let's
back.
know if there's a way to get rid of the parentheses.
So
Every time I
this
type it
should
in-
accept it, right? Oh, I don't want to save it. I want to submit it. So if you get that correct. Question?
Does that show solution always pop up? Because
Yes.
I never seem to see it online.
It does if you get it right.
If it does, if you get it right, and it pops up after the third time you get it wrong.
Oh.
Yeah. So if you get it right, you always get it. So if you go back to study for an exam, and you're like, how did I get this? You can always show a solution. It will show you kind of the work I expect you to have on the exam. So yeah, they don't have.
Confusing. I was like, well, how do you get rid of those parentheses?
Yeah. So it's just saying ln of x plus 1,
Okay.
not ln of the quantity x plus 1.
some people did the same problem in a different way and they still got it right.
You can put it in a different way, multiple different ways. Like what I did in the other class, I put it in, go to students view, this is section, the other class, we worked out this problem and we put it in this way and we got it right, which is equivalently the same, right? Wiley should not have an issue with, unless it says use positive exponents, you should be able to put it in both ways. So if you put it in that way, that's fine. The key here is it's ln of x plus 1, not ln of the quantity x plus 1. All right, so does that make sense on that problem? So today we're going to cover some more of 3.4, so we'll actually go through some of this problems. This is the one I did in class, and it turned out the answer was 1 over square root of pi, and I put pi to the minus 1/2, and it didn't like it. So I submitted the error. It might take them a couple days, or hopefully by later on today. It used to tell me that, okay, it used to tell the students that there's an error on this problem, so, you know, they're fixing it. Now it only does it when they go in to fix it, so they haven't even seen I reported the error yet. So I can go over this one in class and show you how Wiley wants you to enter it. However, it's still correct to write it the other way, and so if you do that, you will get your points eventually. Okay. So last time we talked about related rates, and the important thing in this section is to note x is a function of t, y is a function of t. Pretty much everything that's changing is a function of t. So a lot of times you'll be given problems where you can think of a picture of it happening, like a baseball player running to second base. And think of, okay, if I freeze time, what's changing? Or before I freeze time, what's changing? And then you write those as variables. And when you differentiate those variables, you might have x. The derivative of x with respect to t is dx dt. The derivative of y with respect to t is dy dt. The derivative of theta with respect to t is d theta dt. So you have to be very careful that you don't differentiate x to be 1. The derivative of x is dx dt. The whole point of this is you're having these related rates. So we talked about strategies to solve the problems of related rates. First thing is we need to assign a letter to every quantity. Step 2 is identify what we have in terms of rates. So if I say, you know, the rate in which I blow air into a balloon is given. So then that would be dA dt or dV dt, depending on if it is just a circle like an oil spill, or if it's a balloon, it's a sphere. So then the rate of change is going to be dV dt. It's the rate of change of volume. So they're not going to give you, this is dV dt, this is dA dt. They're going to say the area is changing at a rate of 30 miles squared per hour. So you know that's dA dt. So sometimes you can kind of look to the units to see if it's, you know, if I look at a circle, I have the rate of change of radius, so that's going to be like miles over hours. So it's going to, your units are going to be just the length. If I talk about the rate of change of area, that's going to be like miles squared over hours. Your rate of change is going to be related to an area, that's dA dt. If your rate of change is related to a length changing with respect to time, that's dr dt. And then if I have volume changing with respect to time, that's dV dt. So sometimes you can kind of check your units to see, okay, is this a rate of change of volume? Is my units cubed? Is it a rate of change of area, or my units squared? Is it a rate of change of length, or my units just to the first power? So let's look at an example. So once we get this, we write an equation, which generally is the hardest part. From there, we differentiate it. Step 5 is to plug in all the given information from step 2. You might have to go a step further and find a missing piece, but you'll be given everything to find that missing piece. And then step 6 is just solve for the rate that's asked for. All right, so let's look at example number 3 in your book. These are kind of long worded problems, so I don't want to write out everything, but I want to show you how you're going to be how it's going to, what information you're going to be given, and then how you're going to evaluate that. So, a baseball diamond is a square whose sides are 90 feet long. Suppose a player running from second base to third base has a speed of 30 feet per second. At the instant when he is 20 feet from third base, what's the rate of change of the player's distance from home plate changing at that instant? So, drawing a picture is key here. So if I have a player that's running from second to third, the rate of change, this line is changing, right? If the player's over here, it's longer. And as it's getting closer and closer to third base, this is getting shorter. The distance the player is from home is decreasing. That's what I want to find. So I need to name that something. What would be a good thing to name this line? That's step one. H, right? Hypotenuse. So we can call this H. Or home, the distance from home. Doesn't matter what you call it. So we're going to call this H. It is changing. So I'm going to write that. This player is running to third base. This distance the player is to third base, is it changing? It is changing because the person is running. Now we're going to freeze time when it's 20 feet from third base. And we're going to talk about, at that instant in time, what's the rate of change of this line? This line is, the rate of change of this line is not a constant rate. It's depending on how close this person is to third base. You think of the example of the balloon. If I blow up a balloon, the rate of change is large at first. It's going from pretty much nothing to something. But then after the balloon is so big, the rate of change is pretty small. I'm putting in the same amount of air, but it's not growing at a constant rate. So I always have to talk about an instant in time. I always have to say I'm freezing time, now I'm going to input my information. But this is changing. Now eventually I'm going to freeze it to when the person is 20 feet from third base, but I'm not there yet. You never want to plug in too much information at first. Is this distance changing? No, so it's a constant. So, kind of put this aside and we'll kind of come back to it. So, drawing of pictures is really helpful. So I have this baseball diamond. That's a square, so it tells me this is 90-degree angle. And I have my player running from second to third base. And I want to find the rate of change of H. So this is 90 feet, right? It's not changing. I can write 90. What did we decide to name this distance? You guys want to name it? What? X, O, A. O is probably not a very wise choice because it looks like a 0. A. A is fine. So that's perfectly fine. We can call it A. So what's given in the problem? Well, we notice that, okay, so first let's write an equation. What is the relationship between A, H, and 90?
A squared plus 90 squared equals H squared.
Exactly, using Pythagorean's theorem here. This is a right triangle. That was given because we know it's a square. So I have A squared plus 90 squared is H squared. So we want to decipher what's given and what they want to find. They want, what do they want? dH over dt. They want to know the rate of change of H. Oh, I'm still zoomed in. I was like, man, this is not fitting right. Okay, so they want dH dt, right? What's given? Do I know how fast this player is moving to third base?
Yeah.
So what would that be? The rate of change of A, right? This is frozen.
So dA dt.
Oh, sorry. Yeah, exactly. Given dA dt. What is dA dt? Do you guys remember? It's 30 feet per second. Is it increasing or decreasing? Is he getting closer to third base or further away? So it's going to be negative. And that's kind of something you can think about towards the end. But This is minus 30 feet per second. He's getting closer to third base. So the dAdt is decreasing. The rate of change of A is decreasing. And then when I freeze time, I'm freezing it when A is 20 feet. So this is the information I'm going to plug in after I differentiate. Very key. If I plug in A to be 20, I end up with 0 equals dH dt, which doesn't make sense, right? So you want to be very careful with don't plug your information in until you differentiate it. So let's differentiate this function. I'm differentiating with respect to t. What's the derivative of A with respect to t? A squared. Very good. 2a dA dt. What's the derivative of 90 squared? It's 0, correct. And what's the derivative of h squared with respect to t? Good. And I want dH dt, right? So I can solve for dH dt. It turns out dH dt equals a over h times dA dt. So I just did algebra there. If I divide both sides by 2h, the 2's cancel, I have a over h times dA dt. You guys see that?
Oh,
Right? So now I want to evaluate on what's given. So I know A is 20, and I know dA dt is minus 30. What's H?
So we gotta put it back into the regular.
Exactly. So to find H, come up here to the original relationship given and plug A as 20. So I have 20 squared plus 90 squared equals H squared. So it turns out H is a weird number, which is like 10 square root of 85. So sometimes you have to go back to the original relationship and plug in something that's given to find the missing piece, right? The rate of change of H depends on A. It also depends on H, and it depends on dA dt, which makes sense, right? It depends on how fast you're moving, where you're at, and then also the distance from home plate. But A and H are related. If you know A, you can find H. If you know H, you can find A, right? So I can solve for H by plugging 20 back into my original expression and solving for H, which is 10 squared of 85.
So did you use A and H because they're both changing?
I need to find A, dA dt, and H to plug it in this relationship.
Okay.
I was given A because I freeze time when my baseball player is 20 feet from third base. So I know I called A the distance from third base. So then A would be 20. dA dt is how fast he's going at that instant in time, and I know that's minus 30. So H, I need to find H to plug this in here. So to find H, at that instant in time when I freeze it, I know that this is 90 and this is 20. So I can find H by using Pythagorean's theorem, and that becomes to be 10 to the square root of 85.
And then you plug it in.
Then I have everything I need to find dH dt, so I just plug that in. So dH dt is 20 over 10 square root of 85 times minus 30, which gives me minus 6.51 feet per second. So I'm getting closer to home by 6.51 feet per second. Question?
The negative 30, you mentioned that he's arriving at a destination.
Yes.
Is that essentially like on he's approaching the origin?
Yes.
That's why it's negative.
Yes.
Okay. So
And
if
you
it
can
was the other
also,
way around, like if it's like
if he's running away from
how
this, then
fast
you
is he
pause
going
it.
after
Yeah.
this much distance or
Yeah, and a lot of times it will say the rate of change is increasing, so you know it's positive. The rate of change is decreasing, so you know that's negative. But sometimes they'll say a balloon is deflating at a certain rate.
Or like a, okay.
So you know that the balloon, so that the rate of change of volume is negative because it's decreasing. Does that make sense?
Yeah.
So sometimes you get these keywords in there like increasing and decreasing,
Okay.
or he's getting closer to something. Another problem we'll do a lot is these ladder problems. A ladder is leaned against the wall. If I want to talk about the rate of change, the height of the ladder, it's going to be negative because it's getting closer and closer to the bottom. But if I want to talk about how fast the bottom of the ladder is moving away from the wall, that's going to be positive because it's moving away from the wall. Oh, it's moving away from this point of origin type thing. So if it's going this way, it's positive. If it's going this way, it's negative. So it'd say the ladder sliding down the wall at a rate of 3 feet per second. You would know that's going to be minus 3 feet per second because it's decreasing. But if it's saying it's moving away from the wall at a certain rate, you know it's going to be a positive rate. Which
It just kind of depends on which end of the ladder they're talking.
exactly. And a lot of times you can think at the end as saying, this person is getting closer to home, so my answer is going to be negative. Sometimes you can pull out all the negatives and decide at the end, is it increasing or decreasing?
Okay.
So if it was respect to second base,
It would be positive, yeah. So yeah, if it would be, what's the rate of change at second base? It'd be positive because it's going away from that. So the rate of change is increasing type thing. The distance is increasing. Question.
Like the DA, DT,
Mhm.
like explain.
DADT is given. So it tells you that the speed of the person running from second base is 30 feet per second. So you should be able to read that and say, okay, that's the rate of change of A, because I named A this distance here. The distance from second base to third base is called A. So the rate of change, how fast that person is moving, is DADT.
So how is, then what's the DH?
DHDT is what you want to find. That's the rate of change from the person from home plate. How fast is this person getting to home plate? What's the rate of change from the person to home plate? That's
How
DHDT.
is he running 30 feet per second?
He's running 30 feet per second to third base. That doesn't mean he's getting 30 feet per second to home, because home is not, he's not running in a linear fashion to home. He's running linear along this line. So the rate of change of X, or the rate of change of H, is going to depend on A, H, and DADT, how fast he's running. So this is your relationship of your rates of change. So here, the rate of change of H is dependent on A, H, and DADT. So once you know those three, plug it in. And here, it's minus 6.51 feet per second. So he's getting closer to home at this rate at the instant in time he's 20 feet from third base. Because you can only talk about it in one instant in time, right? Because the rate's not constant. It's constantly changing. So the rate of change here depends on where he's at, because if he was over here, the rate of change would be different, because A would be a different number. And then H is also dependent on A, so that would be different. And how fast he's going at that instant. Once you know all three values, you can find the rate of change from where he's at to home base at that instant in time. So let's look at another example. It's a similar type setup. And this is number 4 in your book. Example number 4. So let's look at the wording of this. So we have, sometimes in the setup they give you the figure, but you're very rarely given the figure on an exam or a quiz. So it turns out being able to draw what's going on is worth points. So definitely if you know it's a triangle or there's some kind of relationship, you'll get a couple points for drawing that out. So in this example, we have a camera mounted at a point 3,000 feet from the base of a rocket launching pad. If the rocket is rising vertically at 880 feet per second, then when it's 4,000 feet above the launching pad, how fast must the camera elevation angle change at the instant to keep the camera aimed at the rocket? So we have this problem that this rocket is going up in the air, and I have a camera that's 3,000 feet away from the launching pad, and I have to set it on a tripod that's going to be able to increase at a given rate to record this rocket going up in the air. Because at first it's going to increase a lot, right? And then after it's up there for a while, I'm not going to have to increase that fast. So they give you this setup. I have the camera. It's 3,000 feet from the launching pad. This 3,000 is not changing. I have the elevation angle, and I have the height of the rocket. Now, here they work out, they call phi, is that phi? Greek letter? Theta is the other way, phi is straight down. Okay. Phi, the camera elevation angle, they say we're going to call that phi, and h is the height of the rocket. So what would be a relationship to phi, h, and 3,000? Tangent of phi is h over 3,000, right? So I have, it's kind of drawing this here. I know I'm kind of zoomed in still. I'll fix that in a minute. Phi, 3,000 feet, and h. H is changing and phi is changing, but 3,000 is not changing. So my function here, tangent of phi, is h over 3,000. So what's given and what wants to be found? So what's given? 3,000 is given, but that's not changing, so there's no rate there. What's this 880? What?
So that would be 8.
That's the rate that it's
It's a rate, right?
trapped.
So dH dt, right? Because we named this h. So yeah, this is dH dt. So this is dH dt. And it's increasing, right? It's going away from the launch pad. So that's positive. Go ahead and zoom out so we can see what we're doing. Okay, so then we also have, we're going to freeze the instant in time when the rocket's 4,000 feet in the air, right? So that's just h. What do we want to find? The rate of change of the angle of the camera, and we name that phi. So we want d phi dt. Okay, so that's pretty much everything that we have. So now it comes the calculus. The calculus is differentiating the function, solving for d phi dt, and then finding any missing pieces that we need. It turns out we're going to have to use some trig here. But that's not too scary, right? Okay, so now I need to differentiate this function with respect to t. What's the derivative of tangent of phi with respect to t? Good. Good. Very important that you take the derivative of the inside because that's a rate of change we want to find. If you don't, you won't have a d phi dt to solve for. And what's the derivative of h over 3,000 with respect to t? You could do the quotient rule, but 1 over 3,000 is a constant, right? What would be the derivative of 5h with respect to t? dH dt, right? So the same thing if I have 1 3,000 out in front. The derivative of 1 over 3,000 times h with respect to t is 1 over 3,000 dH dt. That's just a constant, right? So I have 1 over 3,000 dH dt. I want d phi dt, right? So if I solve for d phi dt, I have d phi dt equals 1 over 3,000 times secant squared of phi times dh dt. Right? So what am I given? I'm given dh dt, which is 880 feet per second. I'm given h, which is 4,000. I need phi, right? So just like we did before, if I plug this into my relationship, I have tangent of phi is 4,000 over 3,000, which would be 4 over 3, right? So if I draw a picture here, I have 4, 3, this is a 3, 4, 5 triangle. 3 squared plus 4 squared is 25. Square root of 25 is 5. So you could go through and show that, right? 3 squared plus 4 squared is 5 squared. Or you can know it's a 3, 4, 5 triangle with that relationship. I just did the Pythagorean theorem here to find this is angle from this relationship. I know that this is what this triangle looks like. Right? If you're given two sides of a right triangle, you can find the missing side by using Pythagorean's theorem. So I'll let you guys catch up on a minute. Does everyone understand here?
Why are we finding it?
I need to know what phi is so I can find secant of phi squared. Because, right,
Okay.
dHdt is given, so I'm good there. And h is given, but the h doesn't help me because the relationship with d phi d theta depends on phi and dH dt. So I have to use this back into the original equation, and if I do that, the original equation gives me this tangent of phi is 4 over 3. So I want to know what secant of phi is. So you can see how the trig that we did on the Are You Ready for Calculus comes in. If I tell you tangent of phi is 4 over 3, I ask for secant of phi, you need to know that so you can plug it in a problem like this. Does everyone understand where I get tangent of phi is 4 over 3? So from here, I drew this picture to find the missing piece, and the missing piece was 5. So now I'm going to look at this picture and plug that in to find what secant of phi is. So now doing this, I have d phi dt is 1 over 3,000. What's secant of phi? Secant is 1 over cosine. Cosine's adjacent over hypotenuse. 5 over 3. Very good. And that's squared. That's no big deal. Times dH dt, which we know is 880. So if I plug that in, I get 0.11. But my answer is in radians per second. Anytime you differentiate a trig function, you plug in a value, you always get radians. So if they want you to convert it to degrees, what do I need to do to convert radians to degrees? I need to cancel the radians. So 180 over pi is converting from radians to degrees. And if I do that, I end up with 6.05 degrees a second. There's a lot to these problems, right? So the rate of change here, at the incident time when the rocket is 4,000 feet in the air, the angle that the camera has to change is roughly 6 degrees a second. All right.
Is there a quick way to check our answer? In the end, I want to make sure that my answer is correct. So how can I?
To plug it in, you mean?
Yes.
Not that I can see. Because if you get the wrong answer by doing the wrong algebra, you plug it in, the left side should equal the right-hand side, but you might not have the right derivative. So not really. In the back of the book, you'll have all your odd problems, so you should be able to check that. So let's look at some Wiley problems here. Oh, sorry. You guys need a few minutes on this? See if I can open it. Okay, so this is section 2. We're going to look at 3.4. The first one's pretty straightforward. So let's go look at the first question here. Are you guys done with the writing? I'm going to pull this up. Pull this down here. Okay, so 15, okay. So we have this question here. We're given an equation, and they tell you both x and y are functions of t. So if I differentiate x, I don't get 1. I get dx dt. Then they give you this relationship. It doesn't necessarily mean anything, or it could, depending on what's going on here. And they ask you to find dy dt given dx dt is 7 and x is 2. So we're freezing an instant in time when x is 2, and the rate of change of x is 7. We want to find what's the rate of change of y. Eventually we'll talk about linear approximations and differentials. If I change x very much, how volatile is y? If I change x a little bit, how much does y change? And so this is going to be used later on to kind of compare the rates of change to y to the rates of change of x. So differentiating this function, find dy dx, and then plug in dx dt is 7 and x is 2, and calculate the value, the rate of change of y with respect to t. So this is 3.4, number 1. So let's look at this problem. So given this relationship, if I differentiate it, I get dx dt plus 2 dy dt equals 0. You guys see where that comes from? Now if I solve for dy dt, this is just algebra, moving dx dt to the other side and dividing by 2, I get the relationship that the rate of change of y is dependent on dx dt divided by 2, minus dx dt over 2. Dx dt was given, so if I plug 7 in, I get minus 7 over 2. It doesn't depend on x. They give you an x, but it doesn't depend on x. The same thing with dx dt. This is the rate of change of x with respect to t. So if y dy dt is changed by 10, then dx dt has an output of change of minus 20.
So where did it come from?
What?
Thing.
It came from the problem. So this next one is saying find dx dt given dy dt is 10. X equals 1. The common mistake in this problem was to say, oh, x is 2, I plug 2 in. you get dy dt is 0, right? Because the derivative of 2 is a constant. Yeah. You never want to plug in what's changing before you differentiate it, right? Because if I differentiate x, I get dx dt. That's the rate of change. But if I differentiate 2, I get 0, and I don't get that rate of change.
Can you go back to the
Yeah.
one for just a second?
How did you get the bottom one?
Here.
Okay, so.
So now if I want to solve for dx dt, I subtract this to the other side, so I get minus 2 dy dt.
Okay, so.
Yes.
On that second part where it says x equals 1, where does that come into play?
It doesn't.
Okay.
Because the rate of change doesn't depend on x or y. It only depends on dx and dy.
So why does baby give that to
In a different variation of the problem, it might depend. If this was x squared, then when you differentiate it, you get 2x dx dt. So rewriting it, this could be a function of x. Could be a function of x. Could be a function of x, y, and dy dt.
And that's
Depending
when
on,
you plug that
and
in.
that's when you would plug in what x is. And you might need to plug x in the original expression to find the y. Plug it in. Question.
Why does dy dt equal 10?
Yes.
It's given.
Are you?
It's a second part of the problem. So it says, so I did 2 parts here. I found dy dt given the information here, and I found dx dt given the information here. And it said dy dt was 10. So I did 2 separate problems there.
Sorry, I didn't see the other part.
No, I don't know if I really showed it, but. So you see here, I'm asking for, I'm finding the function, or I'm finding the value for dy given dx is 7, dx dt is 7. Here I'm finding the function or the value of dx dt when dy dt is 10. Eventually this is saying the change in y with respect to time was 10. That would result in a change in x that turns out to be minus 20.
So why is x given in the first place? Because that's the exact value of y.
Because it could, because this is where I'm freezing time. I'm freezing time when x is 1. Turns out when x is 1, dy dt is 10.
So that's where you did that.
And it turns out you might use this in a case. If it came out to be like an x squared, then you're going to have an x to plug in. When you differentiate x squared, you get 2x dx dt. So you have here differentiating x, you just get dx dt, and it doesn't. You don't have an x to plug in.
Okay.
So let's look at an example
Or we have to use that.
where we have to use a potential something we don't have, so we have to find it. So we don't have too much time, but hopefully we can get through this one. I've seen this one very similar on the final exam with this oil spill problem. So we have an oil spill from a ruptured tanker spreads in a circle whose area increases at a constant rate of 4 miles squared per hour. So that, what does that tell me? What is 4 miles squared per hour? That's the change in area. So that's dA dt. How fast is the radius of the spill increasing? So that kind of tells you it's going to be positive. And that's dr dt. Specifically, when we freeze time, when the area is 4 miles squared. So can you guys kind of see this? I'm pouring in oil into the water, and my circle is spreading out at this constant, or the water is going, or the oil is going in the water at a constant rate, and it's growing. And I freeze time when the area is 4 miles squared. And I say, at that instant in time, how fast is the radius changing?
So the increasing there doesn't mean it's positive?
Increasing means it's positive. It kind of gives you a heads up that it's going to be positive. The rate of change is growing. The rate of change is positive rate of change because the circle's increasing versus decreasing.
So that,
So
so the first like equation, 4 miles, well, not equation.
So what's an equation to relate area of a circle to radius? Yeah, right? So I have area is pi r squared. So if I differentiate that with respect to t, I get dA dt is pi to r dr dt, right? Pi is a constant. So I want dr dt, and I'm given dA dt. But one extra step, you're also given the area is 4 miles squared. So you need to find r. So if you plug it back in here, you can find r. It turns out r is 2 over the square root of pi.
That where you're on the left there,
Mhm.
that's pi, is that pi squared r or pi squared?
Here,
Yeah.
this is 2r dr dt. Because the derivative of r squared is 2r dr dt.
Right.
And I know we're running out of time here, so we'll finish this example tomorrow in your take-home quiz. So. I will send an email out later today with the attachment of the ways that you can enter your documents and for anyone that's on class. Take home quiz is doing class tomorrow.
There is no function inside, function inside.